To begin with this lesson, we are going to be solving equations. But to start, I'm going to have you go ahead and solve this equation. Go ahead, take a moment, pause the video, and find theta. So for this problem, we have a right triangle trig situation. So we have cosine of theta equals 0.6. So if I want to know what theta is, I have to undo cosine. So we do the inverse cosine of 0.6, and then we get our answer. If we wanted, or if our calculator was in degrees, we get our degree measure to be 53.1 degrees. And if we're working in radians, our radian measurement would be 0.927. Again, remembering that a lot of things that we're going to work on are going to be in radian form because we're looking at that precision piece and trying to keep values exact when we can. But for this one, we just had both of the answers. So what we're going to do is a very similar problem in today's lesson. We're going to be solving. But now, instead of getting these decimal approximations, we're going to be using our unit circle. Now, sometimes, don't get me wrong, we will be doing decimal approximations as well. But when we can find those exact values, we will. If we don't tell you what we want our measurement is, typically want it in radian mode. So in this case, I'm going to find theta in radians. Unless I tell you that x is between 0 and 360 degrees, then I'd be giving it in degree measurement. So for this problem, this would be a no calculator question. So now I have to think about my unit circle, and I want sine. So thinking about sine is that height, that's the y value, and it's a half. And that, remember, is the short height. So therefore, it's in those two quadrants at those locations. So therefore, theta is pi over 6. That's this, and then we count around, and this one is 5 pi over 6. And that's just between 0 and pi. However, we can keep going around the unit circle. So I can go around to here, and it could be this angle. So that's pi over 6 plus another 2 pi around, because that's that full cycle around. So then that would be 13 pi over 6. Because if I'm going to go around that full time, that's 2 more pi, which is 12 pi over 6. And then here, I'll change colors here. If I went like this, that's over to that direction, that ends at that same spot. It has the same height. So 2 pi past 5 pi over 6 is 17 pi over 6. And then I can add 2 pi again. So I can add 12 pi over 6 to this, and I get 25 pi over 6, etc. Don't forget about negative. I can go this way around. So that's negative pi and another pi over 6. So that's negative 7 pi over 6. And then I can go around negatively to here. That's 1 pi over 6 short of 12 pi over 6. So that's negative 11 pi over 6. So what we're doing is we're solving this equation for theta. It's not just finding one measurement. This one here, we found one measurement. We found where the cosine of what angle is 0.6. So that ends up being right here. But there's more than that. There's this angle here. Cosine is also positive 0.6 here because cosine is your x value, and then multiple times around the unit circle. So that's part of what we're going to take into consideration today. So just finishing up this problem here. So therefore, there's all these dots in between. It also keeps going this direction as well. So the way we can write this is theta equals pi over 6. That's the easiest one. And then it happens again every full cycle, which is 2 pi k. And k is the number of times it goes around the circle. So if I went 1 time, that would be plus 2 pi k. 2 times would be plus 4 pi. 3 times would be 6 pi. So that's why it's plus pi k, to take into consideration those full revolutions. Or if I went negatively around, that would be a negative 1, negative 2, etc. So those would be negative values. Okay, so that's the first one with pi over 6. And then second one is 5 pi over 6, again, plus that 2 pi k. That takes in consideration all values. Since I told you to solve and I didn't give you any kind of restrictions, these would be both of my answers. If I said between 0 and 2 pi or something along those lines, I may clue you into what I'm actually looking for. So this is kind of the basics of what we're working with, and we're going to make these equations a little bit harder. So here I already had it solved for the sine of theta. In the next example, it's not solved for the sine of theta, or in this case, the cosine of theta. I have to rewrite my equation so I can get everything on the one side besides my trig function. Then we'll do some substitutions as well. Okay, so if I give you this problem, what do you think of doing first? Add the 1, divide by 2. Again, you're getting the cosine of theta by itself. So adding the 1 and dividing by 2. So I have to figure out where does the cosine of theta equal a half. And I told you here my restriction is between 0 and 2 pi. So I'm just looking at this one revolution around. So cosine is a half. Cosine is x. A half is short. So that's your short length, which happens here and here. So at this angle here and at this angle here. So therefore, that's when theta is, so this is 1 pi over 6, 2 pi over 6, which is pi over 3. 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, which simplifies to 5 pi over 3. Again, you're not going to get a filled out unit circle for these. You're not going to have time to fill out a unit circle. Draw yourself a little picture and go from there, keeping in mind that you're counting around by pi over 6 and then also that pi over 4. Okay, the next one. Now for this one, I did not give you any values to go off of, but so for this, I need to solve. I have more than one trig function though. When I use my unit circle, I can't have 2 different trig functions. So I may have to rewrite it. I may have to do some substitution. This unit or this section is called trig identities. I may have to use some identities that I know, some of those things. So right now you're getting comfortable practicing with these and you just have to rewrite things. And you're going to see a lot of different examples both in the lecture piece here and then also in your homework. Because the more you start to see things, the more you start to look for them as well. So if you see a sine of theta and a cosine of theta, probably the one thing that you start to think about is you know that tangent to theta is the sine of theta over the cosine of theta. So it's the y value over your x value. So if I can get this division, I can replace this with tangent. So that's one of the things that you can kind of think about. And again, I need sine on top. So I'm going to move the sine over and we're going to see what happens. So I add the 3 sine of x over. And then I need to get sine over cosine, but I have this 3 and 4. So what I'm going to do is I'm going to divide both sides by the cosine of x. So that cancels out. But I also need to get rid of that 3, so I'm going to divide both sides by 3 as well. Get rid of him. So now what I have is 4/3 equals the sine of x over the cosine of x. And we know by definition, the sine of x over cosine x is tangent x. So I can substitute the tangent of x in place of that sine x over cosine x. And on the right side, that equals 4/3. Okay, so 4/3 is not a measurement on your unit circle. Just like our warm-up, 0.6 was not a measurement on the unit circle. So I have to go to my calculator to figure out what my angle measurement is. So I'm going to have to do inverse tangent. When I do inverse tangent of 4/3, we end up getting 0.927. Okay, so again, we're doing radian measurements. So now, just like before, we have a lot of measurements where they are the same. So it's not just one solution or 2 solutions. There's an infinite number of solutions. And since I didn't tell you anything, I have to list that out for you. Tangent's a little different than sine and cosine. Tangent occurs, sine and cosine occurs every 2 pi around. So every 2 pi it repeats itself. But do you remember what tangent's period is? How long does it take for tangent to repeat itself? Pi. So tangent repeats itself every pi. So therefore, instead of adding 2 pi k to this, we are going to add pi k, where again, k can be either positive or negative. If they just asked between 0 and 2 pi, again, if I restricted the domain, if I said this went from 0 to 2 pi, if I said my domain was restricted there, then it would be 0.927. Then I'd add this pi to that, so I'd add that 3.14, which would give me 4.07. If I added pi to that again, now I'm too far. I'm past 2 pi, which is 6.28. So then I would be over it. Okay, another one. So this is that restriction here. So here's another way to look at your restriction. So I'm giving you a domain restriction. And so now I have this mess here. So again, I have sines and cosines, but I don't just have a sine of x and a cosine of x. Okay, I have a cosine squared and then a sine of x. So it adds in that level of complexity. So I wrote before the formula that we know for tangent. So tangent of theta is the sine of theta over the cosine of theta, but I have some other trig identities. One of those being the Pythagorean identity, sine squared theta plus cosine squared theta equals 1. If you see sine squared theta plus cosine squared theta, that's a form of 1, and you can just pull that out and just put a 1 in there. But there's no sine squared of theta. And I can't square both sides because then I end up getting a fourth, and this becomes messy. So there's no way that I'm going to get this out of here. But what I can do is I can do some substitution to make this problem a little easier. So I have a cosine squared of theta. We'll solve this for cosine squared theta. Just subtract that sine squared of theta. So now we're going to substitute that in place of the cosine squared of theta, because we said cosine squared of x equals 1 minus sine squared x. So we have this 2 here, and now we can replace 1 minus sine squared x equals 3 minus 3 sine x. Still not nice. So this is not an easy problem, but you've got to be able to do the substitution or you can't even start the problem. So I go ahead and distribute that 2 through, so I get 2 minus 2 sine squared x equals 3 minus 3 sine x. Let's see the squared here. So I have a sine squared and a sine, and I have some constants. This is what's called quadratic in nature. So I'm going to get it set equal to 0. Since this has a negative coefficient, I'm going to move everything from the left to the right. So 0 equals 2 sine squared x minus 3 sine x, and then I'll subtract that 2 over, which gives me a 1. And at this point, sometimes you can just see it, but if you can't, let's do this thing called u substitution. Okay, so we make u what's hard. That's the sine of x. So when I do that, back to the problem, I get 0 equals 2. So instead of the sine squared of x, I replace the sine of x with u, but it's still squared. And then minus 3, instead of the sine of x, I put in a u plus 1. And I can factor that. Do diamond and box if you need to. But it's 2u minus 1 and u minus 1. And then I set those equal to 0. So I get u equals 1/2, and I get u equals 1. Yay, we have u. But we're not done. Now that I know what u is, I go back to my u substitution. So the sine of x equals 1/2, and the sine of x equals 1. So look at your unit circle. Where does the sine of x equal 1? Again, a 1/2. That's the short side. Sine is up. And this is between 0 and 2 pi. So 1 time around the unit circle. So what's this angle? Pi over 6. And what's this angle? 5 pi over 6. And then where does the sine of x equal 1? So where's my height 1? That's right here at pi over 2. So those are my 3 values that are my solutions to this equation. A couple more examples. So again, I'm just trying to expose you to as many different types of questions that you're going to see when you're working with solving trig equations. Our goal being that we can use our unit circle as much as possible, knowing that sometimes we cannot. And this is one of those cases where we're not going to be able. So for this problem, since there's only one trig function, we're going to go ahead and isolate that trig function. So we're going to subtract the 2 over. Divide both sides by 5. Now once we get here, this 3x, I can't get the 3 out from inside here because it's the cosine of this angle. So this is like 3 times whatever my x value is. That's the angle I'm looking at. So what I typically will tell students to do is, because sometimes it's hard to see that, you may want to just do a u substitution for it so that you can solve it like normal. So then when I do that, so I get the cosine of u equals 2/5. Is 2/5 the value on the unit circle? Nope. So we're going to have to go to our calculator. So we're going to inverse cosine 2/5 to try to find what that angle is. So that's 1.159 is what u is. But that's not what the actual angle is, that's what u is. u, remember, is 3x. So now I go back into that spot there, and I know that u is 3x, so therefore 3x equals 1.159. Okay, but I also have to go back and look at, so from here, cosine is 1.159 radians. So that's about here. So that's also about here. So now I have to think about where that falls on the unit circle. So since this angle right here is 1.159, I know that this angle right here is also 1.159. So then I know my other value, I know that my other value is going to be 2 pi minus that. Minus, okay, because this is 2 pi, so it's short this much. So that's my other u value. That's my u value. Okay, it's not my x value. So then when I subtract this out, I get 5.124. So that's my other u value. But again, that's u. It's still 3x equals to that. Okay, so pause for a second and take a look at each of the steps that we've done. Again, knowing that there's so much of this that's just a little bit different, but just to make sure that you understand where things came from. And again, remember we were finding what the cosine of that angle was. So remember, cosine's period is always 2 pi. So this happens every 2 pi k for both of these. And you may be thinking, why are you writing plus 2 pi k? I restricted the domain. But even though I restricted the domain, it still could happen more than one time because my period changes. The period for this function is 2 pi over b, and b is 3. So it's actually 2 pi over 3. So when I solve this, I get x equals 1.159 divided by 3 plus 2 pi over 3k. And then on this one, 5.124 divided by 3 plus 2 pi over 3k. Because again, the period for this function is 2 pi over 3 because my b value is 3. That goes back to some of your Algebra 2 type of work when we were looking at how often things repeat. So I type this into my calculator, and I get 0.386 plus 2 pi over 3. Okay. And 5.124 divided by 3 is 1.708 plus 2 pi over 3k. And my value has to be between 0 and pi. So this value is between 0 and pi. This value is between 0 and pi. Remember, pi is 3.14. So now I have to type this into my calculator and add it and see if I'm still under pi. Because if I am, I have to list that as well. And I am. So therefore, it's 0.386. When I add 2 pi over 3 to this, I get 2.48. And then 3 significant figures, 1.71. And then if I add 2 pi over 3, I get past 3 pi. I'm sorry, I get past pi, 3.14. So these are my 3 answers. Next problem. Again, exposure. We expose you to as much as we can so that you can start to find some patterns and things to look for. So in this problem, the first thing hopefully you notice is there's more than one trig function. So therefore, I either have to get it so that I have a tangent, or I have to be able to do a substitution. Since only one of them is squared, I'm going to think about that sine squared theta plus cosine squared theta equals 1 relationship. Because I know the cosine squared of theta is 1 minus sine squared theta. And this is a substitution you're going to have to look for. Because there's a sign here, I'm going to the substitution, and most likely I'm going to get a quadratic when that happens. So I replace the cosine squared of x with 1 minus sine squared. So I get negative 2, 1 minus sine squared x minus the sine of x plus 1 equals 0. And then I gave you this piece here from 0 to 4 pi. So I'm going to have a list of these. Okay, distributing that through, I get -2 plus 2 sine squared x minus sine x plus 1 equals 0, which gives me 2 sine squared x minus the sine of x, and then minus 1 equals 0. When you see this, a sine squared, a sine, and a constant, you always have to think about factoring, and we're going to let u equal the sine of x. Again, this is something that you do all the time. So I get 2u squared minus u minus 1 equals 0. This is the easy part. This is where you factor. We get these types of factors a lot because these are values we can use our unit circle with. So when I solve, I get u equals -1/2, and I get u equals 1. Remembering we're not solving for u, we're solving for x. So the sine of x is -1/2, and the sine of x is 1. Use that unit circle that you have in your brain. Sine, height, -1/2, short. So that's there and there. So that occurs at 1, 2, 3, 4, 5, 6, 7 pi over 6. And then 1 short of 2 pi, which is 11 pi over 6. And then that keeps going for every pi, 2 pi k. And then here, for the sine of x equaling 1, unit circle, sine height, 1 right here at pi over 2 plus 2 pi k. And then for this problem, I did tell you that we are going from 0 to 4 pi. So no negatives, so I don't have to worry about going backwards. So now you can just list them out until you get 4 pi. Okay, think about what your fraction is if you just keep going with your fraction. So since these are pi over 6s, that's 12 pi over 6 each time you're adding and subtracting. So until you get something that's more than 4, you just keep going. So 7 pi over 6, 11 pi over 6. I'm going to add 12 pi over 6 to 7 pi over 6, which is 19 pi over 6. Well, 19 pi over 6 is less than 4. And then I'm going to add 12 pi over 6 to 11 pi over 6, which gives me 23 pi over 6. So 23 pi over 6 divided by 23 pi divided by 6 is less than 4. And then if I add another 12 pi over 6 to 19 pi over 6, now I'm past. So I have too many. And then I'll keep going over here with pi over 2. Since it's pi over 2, I'm adding 2 pi, which is 4 pi over 2. So then that's 5 pi over 2. And then if I add it again, I get 9 pi over 2, which is too far. So those are all my values. One more example. Solve for the sine of 2x equals the square root of 2 over 2. So I already have it solved for sine. See if you can start this one without me doing any work. Okay, pause it and see what you can do. Okay, so I have to know where my values are the square root of 2 over 2. So the square root of 2 over 2 are always at those 45-degree increments. So that's right there. And it's positive, so that's right there as well. So now I'm looking at where my heights are, those values. And again, instead of the 2x, we're going to just make that a u. And then we'll come back and we'll work with the fact that it's 2x. So the sine of what angle is the square root of 2 over 2? So that's at pi over 4 plus 2 pi k. And then it again happens over here, which is at 3 pi over 4 plus 2 pi k. But that's u values. Those are u's. So now I go back to my 2x and I set my 2x equal in there. And I do the same thing on the right one, 2x. And then I divide everything by 2. Dividing by 2 is the same thing as multiplying by 1/2. So that's pi over 8 plus pi k. So the period for this is pi. And based on the problem, they said from 0 to 2 pi. Again, sometimes you do have to go backwards with it. So pi over 8. If I add pi, that's 8 pi over 8, so that's 9 pi over 8. And if I add pi again, which is 8 pi over 8, that's 17 pi over 8, which is more than 2 pi. So I'm done there. I'll pick up the next one, 3 pi over 8, add 8 pi over 8 to that, so that's 11 pi over 8. Add 8 pi over 8 to that, now you're too far, then you're finished. So those are your 4 solutions that fall between 0 and 2 pi. So to quickly summarize, we just did a lot of problems here. This was just your regular basic equation, solving, getting what your angle measurement is, but now we added on this plus 2 pi k piece. Okay, going around positively and negatively. And then this next one, we had to do a little bit of work to get it to look like that. Here I had both a sine and a cosine. So since I had them and they had the same degree, I could rewrite it with a tangent. Here I had cosine squareds and a sine. They didn't have the same degree on them. So we did our substitution with our Pythagorean identity. And then don't forget to do that U substitution along the way. Here I then started to set the part that's inside with that's part of my angle, that BX part. I made that into a U. So whenever there's anything inside the argument to my cosine, we can make that a U substitution just to make it go a little bit easier. Again, remembering plus your 2 pi k. And when I have that multiplier in there, it's always going to change the period because the period is always 2 pi over b. And since b is 3, it's 2 pi over 3. We moved on. Here was another substitution with the Pythagorean identity because one was a cosine squared, one was a sine. And then here a little bit more with that U substitution piece. So you're going to work through practice problems with this just to make sure that you have a really good understanding of solving our trig functions using the idea from our unit circle, not necessarily using your calculator. Sometimes we do have to use our calculator, but a lot of times we do our unit circle.